morning everyone. Today we are going to have the first lecture of my course entitled Intelligent Control of Robotic Systems. The first course is named as Robotics Primer, where we are going to see robot anatomy and terminologies. The outline of this lecture will be as follows. First we have the robot anatomy, which includes joints and links, and then the terminologies, which will entirely focuses on the work volume and the degrees of freedom. Then we have the main components of the robotic systems, which are actuators and sensors. In actuators we are precisely going to see electric actuators and smart actuator. Then in the sensors will be confined to optical encoders and force sensor. Coming to the robot anatomy, a robotic system is composed of joints, links, actuators and sensors. So there are various robotic systems: a humanoid robotic system, an exoskeleton meant for the movement of the limb of human beings, and medical robotic systems, which will be helpful for minimal invasive surgeries. First, let us take the humanoid robot, where we have the links or rigid and the actuators, mainly electric actuators. And we can see that the exoskeleton meant for rehabilitation purpose also have the links and the actuators. The links in the case of humanoid robots are basically straight links, straight rigid links or serial links you can say. Whereas in the case of exoskeleton, in the schematic you can see it is basically composed of link is basically a series of mechanisms. Here we have 4-bar mechanisms connected in series, and the joints here in the case of the medical robotic system represent a prismatic joint, and thus robotic systems include several joints and different types of links. Different types of links, I mean rigid links as well as flexible links. Now coming to the types of joints of a robotic system, the first simplest most joint is a revolute joint, which has 1 degrees of freedom. What is the degrees of freedom? We are going to see in the upcoming slides. So the revolute joint has 1 degrees of freedom, where the joint variable is represented by theta and d. Q is the joint variable and theta is a joint variable for revolute joint, and d is the joint variable for prismatic joint. As I told earlier, the revolute joint has 1 degrees of freedom, where the variable is a rotational joint angle. It is mentioned here as theta. In the case of cylindrical joint, we have a combination of prismatic joint, where the joint variable is the distance d from the origin or from the initial posture, and the second joint variable is the theta, that is joint angle, rotational angle. So combinedly we have the cylindrical joint, and hence the degrees of freedom is 2 for the cylindrical joint, because it has prismatic and revolute joint combined. In the case of spherical joint, we have 3 degrees of freedom, which indicates roll, pitch and yaw. Okay, when we take a coordinate frame, say x, y and z, where x is pointing outside, we can say that the orientation around the x axis can be roll, the orientation around y axis can be pitch, the orientation around z axis can be yaw, and hence this joint represents 3 degrees of freedom. Now coming to the end effector. What is an end effector? It is a special tooling for a robotic system that enables it to perform a special task. That means it is a device attached to the robot's wrist in order to perform a specific task. There are 2 types of end effector. One is called a gripper, in order to perform grasping and manipulating objects task during the work cycle, and another type of end effector is called tool, in order to perform a process called spray painting or spot welding. Now coming to the terminologies associated with the robotic systems. One is work volume, and work volume indicates the volume inside which the robot can perform or position its gripper. That means the given task to be performed for a robotic system must be given well within the work volume. For example, when we consider a 2 degrees of freedom robotic system where this is L1, this is L2. We have two joints here, joint 1 say theta 1, joint 2 say theta 2, and let us say that theta 1 varies from 0 degree to 90 degree, and theta 1 varies from 0 degree to 180 degree. Again I repeat, theta 1 varies from 0 degree to 90 degree and theta 2 varies from 0 degree to 180 degree. So, when we have this, we can say that theta 1 is 0 and you move theta 2 from 0 degree to 90 degree. So, we will have this, and we have theta 1 90 degree. So, it becomes the robotic system becomes like this, and we have the variation of theta 2 moving from 0 to 90 degree. So, what is observed here is right. So, what is observed here is we have this region as a work volume and we have obtained this region as the work volume line. Then you keep this, like for example, you keep here 90 degree for theta 1 and theta 2 is also 90 degree, and then keep theta 2 0 degree and move, you have this one coming into the work volume. And because of 0 to 90 degree variation of theta 1 and you have this theta 2 varying from 0 to 180 degree, you have this portion combined also, and hence this is the complete work volume of a 2 degrees of freedom. Next, this is for a work volume for a 2R planar robot. That means 2 revolute jointed planar robots work volume. Let us say if it is a 3 revolute jointed planar robot, which means this, this and this, L1, L2, L3. So, theta 1, theta 2, theta 3. So, how can we get this type of work volume? That is again obtained by varying theta 1 from 0 to 90, theta 2 and theta 3 varying from 0 to 180 degrees. You will be getting this, and this is the plot obtained from MATLAB, where we have the outer loop being for theta 1 and the nested inner loops for theta 2 and theta 3 respectively, all three varying from 0 to 90 and 0 to 180 respectively. Now, let us see the work volume for standard robotic systems that are used in the industry. First, let us take a Cartesian robot. The moment I say Cartesian robot indicates the joints of the robotic system are made up of prismatic joints, which means the variation of the joint is d, q equal to d, d for distance. That is why when we see the side view of the work volume of this Cartesian robot, we can see a square area. Similarly, the top view is again a square area. That is all because of the Cartesian joints it has. Theta 1 q1 equal to d1, q2 equal to d2. We can see here the functioning of this Cartesian robotic system where all its joints are prismatic. You can see that they move in a straight line, not in a rotary movement. Okay. This is the real functioning of a robotic system taken from Adapt work volume workspace or website, you can say. And now let us move on to, now for the cylindrical robot, which is a combination of both prismatic and revolute joint, we have the work volume seen from the side view is going to be the square area whereas the top view is a circular area, and the real functioning of the robotic system is shown here, which is a combination of revolute and prismatic joint for pick and place application. Next, we can represent the configuration of a robotic system in terms of its independent coordinates q, whereas for the Cartesian robot it is a combination of prismatic joints alone, and hence the 3 degrees of freedom Cartesian robot is configured as P, P and P. That means it has 3 degrees of freedom continuously with prismatic joints. Similarly, for cylindrical joint, you can say that the first joint is a revolute joint, joint variable theta. The second joint is a prismatic joint, which is D1 or say D2, theta 1, D2, and the third joint is D3. And hence, the configuration of the cylindrical joint or cylindrical robotic system is R, P and P. Similarly, for a spherical joint, we can say it is a 3 degrees of freedom. For this robotic system shown here, where we can see theta 1, theta 2 and D3. That is why it is R, R and D, which is P, prismatic. Similarly, for articulated, what do you mean by articulated robotic system? Which means every joint there is meant for rotary motion. It has all the joints of its system being revolute joint, and hence how many degrees of freedom? R, R and R, which means 3 degrees of freedom constituting all the rotary movements. Next, for the SCARA robot, which is selective compliance assembly robotic arm, has 4 degrees of freedom. I add the 4th degrees of freedom. Okay, so that is R, where the gripper is going to be oriented by an angle theta 4, and hence we have theta 1, theta 2, D3 and theta 4. That is why the SCARA robot has 4 degrees of freedom with one prismatic joint for the third joint, rest all are revolute joint. Now, coming to the actuators, which play a vital role in order to move a robotic system. Here we are confined to 2 types of actuators. One is electric actuators or electric motors and smart actuators. So, coming to the electric actuator, which is a fundamental actuator used in robotic system, is a DC motor, where the principle of working is given in such a way that when a current carrying conductor is placed in the magnetic field in such a way that the direction of current passing through the conductor is perpendicular to the direction of the magnetic field, and in that situation a turning force is generated which is perpendicular to both the magnetic field direction as well as the current direction, and this law is given by Fleming's left hand rule. That means when the middle finger points the direction of current and the index finger points the direction of the magnetic field, then the direction of thumb gives the direction of the turning force. And the control of a simple DC motor is given in this video here, where speed is taken into account. First one is, we can say given RPM, say 100 RPM, then 50 RPM, then 30 RPM, then suddenly 80 RPM, then 150 RPM. So, the speed is the desired quantity in order to have the speed of the robotic motor to be controlled. To the desired speed, the motor should rotate. Here the components of the electronic circuitry are power supply, the DC motor and the driving circuitry, which is in order to have the power amplification, because the motor draws more current. So, we need to amplify the power. That is why a power amplifier is used. It is L293 power amplifier, which is a H bridge circuitry, and we have an interface which is basically an Arduino Uno board. Sometimes National Instruments data acquisition card can be used as an interface between the software and the motor hardware. Now coming to the stepper motor, which is basically has two parts, as in the case of DC motor. We have a stator and a rotor. Rotor is, as the name indicates, it is going to rotate. It is the center part, and the stator are fixed in the outer part. And when the stator sit, see this is a combination, which is first combination, and this one is the second combination. When the first combination is excited, the rotor is aligning itself to the excited stator windings. When the second stator winding is excited and keeping the stator windings at 1 off, we can see that rotor is turning 90 degree from the initial case, so that it is now aligning to the excited stator set 2 windings. When all the stator windings are excited, that means stator set 1 and stator set 2 both are excited in the same time, then we can have the rotor aligned exactly in between the stator coils, and hence earlier it was 0 to 90 degree and now it is 45 degree. That means it aligns itself exactly between the stator windings, and roughly 1.8 degree is the minimum step angle of a general stepper motor. In order to increase the step angle, what we can do? We need to increase the number of stator windings, which means that I need to have the accuracy more better than 1.8, which means that I need to have precise movement of a motor shaft. In the case of stepper motor, I need to have stator windings more, so that once the adjacent stator windings are excited, we can have the shaft to be lying in between the stator windings, so that the angle value can be more precise and more smaller in order to achieve that small angle desired value. And here is the circuitry for the stepper motor, and when we connect this, as I mentioned earlier, power amplifier circuitry, interface circuitry, and this motor with the external power supply to the motor driver, we can have the application of the stepper motor shown here, where the system has a part where we can have a medical needling system to be moved up and down. By the stepper motor functioning, we can have the platform coming down and moving up as per the clockwise and anti-clockwise rotation of the stepper motor. Next, we can have the DC servo motor, which is very cheaply available as compared to the cost of DC stepper motor and DC brushless motor. These are the components that are inside the assembly of DC servo motor. We have a inbuilt potentiometer, so that whatever angle we expect to move, the shaft of the DC servo motor will move to that angle exactly. That exact movement is given by the internal potentiometer, which gives the feedback value. And we have a gear train also in order to have high torque for this motor, DC servo motor. And here is an application where we use same DC servo motor in order to have the spinning of this needling system to enter a tissue volume. Exactly, the spinning is done by this DC servo motor. Next, we move on to the smart actuator, where we focus on the shape memory alloy actuator, which is SMA actuator. There are two smart actuators, you can say. One is shape memory alloy actuator, another one is a piezoelectric actuator. Here we confine ourselves to only SMA actuator. It is available in two forms, one is the wire form, another one is the spring form. In two forms this wire actuator called SMA actuator is available. One is wire actuator, another one is a spring actuator. This has a salient feature where its power to weight ratio is high, because its volume is very small. As you can see here, this is the wire actuator, SMA wire actuator. It has a diameter of 0.45 millimeter, and we can say that the SMA actuator is basically a metallic alloy which is a combination of nickel and titanium. It is also called nitinol wire actuator, nitinol actuators, because it is a combination of two metals, two alloys, you can say nickel and titanium. So, the phase transformation happens for this actuator in order to perform the actuation task. That means during the heating of this alloy or the nickel titanium alloy, we can say that when it is heated, the heated actuator can be formed into any desired shape, either a wire shape or a spring shape, and then upon cooling it comes back to twinned martensite, which means that the austenite is high temperature phase structure of the SMA wire, and martensite is the cold phase temperature structure, crystalline structure, you can say. So, when it is heated it goes to austenite phase, when it is cooled it goes to martensite. In the cooling stage it has twinned and deformed phases. That means when it is cooled it comes to twinned martensite, and upon loading it goes to deformed. Upon loading is the time where we do our application, and in the loaded condition, when it is heated it goes to the original shape. By its memory it goes to its original shape, because it memorizes where and which was its original shape. For example, in this example here, application here, where we have a needling system which is actuated by this wire actuator attached to the lateral side of this needle, and when we power it, when we pass current through this circuitry, we have, due to Joule's heating effect H equal to I square R, we have, due to the current flowing through this needling system, we have the contraction of the wire happens, which means that this is the deformed shape of the wire and this is the austenite original shape, and upon heating it comes to its original shape. That is why the length is getting contracted and hence the needle bends, and upon cooling it goes back to its martensite phase. And other application is shown here, where we can see that it goes to maneuvering in the free space. So, this is the needling system we have developed in our laboratory, so that the actuator is attached to the lateral side or surface of this needle, so that we can have this bending of this needle happening, not by a DC motor which is a bulky one, but by a smart actuator which is SMA wire actuator attached to the lateral surface. Now, coming to the final actuator part, which is electrostatic microactuator, which means that the actuators used in the micro robots. One of the most commonly used actuator is electrostatic microactuators. So, the working principle is such that when we apply voltage to the two parallel plates or two parallel electrodes or to a capacitor plates, a force, so called electrostatic force, is developed. Because of this applying potential across these two parallel plates, opposite charges are induced in the two parallel electrodes in such a way that electric potential causes the forces to be induced in such a way that the two plates try to come together. That means the force generated is an attractive force. That is given by the expression 1 by 2 into epsilon s v square by d square, where epsilon is the dielectric medium between the two plates and S is the surface area of the electrode and V is the applied voltage and D is the distance between these two parallel plates. One of the applications that we find this electrostatic microactuator is in the micro robotic system, where this combination or this assembly is called parallel plate comb microactuator used in the micro robotic system. Next, we move on to sensors. We confine to this lecture purely the encoders. So, we are going to see two types of optical encoders here, which are attached to the motor shaft. The first one is the absolute optical encoder, where it has a disc with several tracks. Let the number of tracks be n, and each track will have different coded regions. The coded region is represented by black color here, and the transparent region is not coded one. Now, let us say that this has 4 tracks, the disc has 4 tracks. The outer ring or the outer track indicates, let us say, 2 power 0, and the second outer ring indicates 2 power 1. So, collectively we can get the decoded value in order to get the sector indication. So, you can see the assembly of this absolute optical encoder to a motor shaft will be collectively having this assembly, which means we have a disc. In one side of the disc we have a light source and the another side is a photo detector to receive the light source passing through this white colored region. That means one region is opaque, another region is transparent. So, the light, once the shaft rotates, the disc attached to the shaft also rotates along with the shaft. So, once the sector, one of the sectors passes through this light source region, then accordingly we will get the photo detectors giving the values. Let the outer ring, as I mentioned, is indicated by the value, say coded value 2 power 0. Similarly, second outer ring 2 power 1, and depending on the relative position of the shaft, we get ones and zeros coming out from the photo detector's signal processing unit. So, the decoded value, let us say it is this case, the second shaft or second sector, you can say. This is number sector number 1, this is sector number 2. So, the decoded value for this case is going to be 0 into 2 power 0, because the 0 is indicating this opaque region, and 1 into 2 power 1, here is transparent, here is transparent, here is transparent. Another 3 inner tracks of that particular sector are purely transparent. So, we get the light source passing, the light passing through the this transparent region, and hence the detectors will give value 1 1 accordingly, and hence we can have that multiplied to get the final value coming to be 14 for that particular sector. Now, The angular resolution for this absolute optical encoder is given by an expression 360 degree by 2 power n, where n is the number of tracks. For example, if we have n equal to 13, the resolution is going to be 0.044 degree, and hence the angle is going to be computed as resolution multiplied by the particular number of the sector, that is between 1 to 8192. Now, coming to the next type of this optical encoder is incremental optical encoder. Here this is the shape of the incremental optical encoder. It has n radial lines, and for this optical encoder we have the resolution given by 360 divided by n, where n is the number of radial lines. So, the actual angle is resolution into counted pulses. So, when we have received the pulses from channel A and channel 2, so which means that two adjacent receivers, one receiver gets pulses, similarly another receiver also gets pulses. Let the receiver 1's output be termed as channel A output, then the receiver 2's output is represented by channel B output. If channel A leads channel B's output, then we can say that it rotates in, say, clockwise direction. Similarly, if channel A signal lags channel B, then we can say that it is rotating in the opposite direction or counterclockwise direction. Now, coming to the final part of this sensor, which is force sensor. Generally, the force sensor is made up of a deformable part, which means that a portion of the sensor where the pressure applied area, that means this is the region where the pressure is going to be applied. So, that region we have generally strain gauges occupying the sensor. The principle of strain gauge is given by change in resistance happens by an expression which is R equal to rho L by A, where rho is the resistivity, L is the length of the conductor, and A is the cross sectional area of the conductor. So, by varying any of these parameters rho, L and A, we can have the resistance of the strain gauge changes, and during the resistance, due to the change in resistance, we can have the voltage of the Wheatstone bridge circuitry getting changed. Okay. So, by the Wheatstone circuitry changed, in the null condition we have the bridge is balanced, Wheatstone bridge is balanced, and in the Wheatstone bridge we have only one variable resistance provided by the strain gauge, and once the strain gauge is not having any change in resistance, then we can say the bridge is balanced. Once we have this is coming out as a balance equation. Once we have, say, R1 is the strain gauge resistance changing, we have the bridge unbalanced, and accordingly we have the output voltage V naught that is proportional to the change in resistance of the strain gauge. This value is proportional to the applied force. That is the principle of force sensor in the robotic system. Simplest force sensor available is FSR 402. Its cost is around 200 rupees, and this has been utilized in our laboratory for an exoskeleton grasping an object, where we have in the contact between the object and the fingertip, we have the force sensor being utilized in order to get the force value. So, in this lecture we have seen topics having robot anatomy involving joints, actuators and sensors. Precisely in sensors we have seen encoders meant for positioning, measurement, and force sensors for measuring the interaction of the force from the environment and the robotic end effector. The terminologies we have seen here are degrees of freedom and work volume, and it is required and suggested by me that you can solve for the 3 degrees of freedom planar robot how I could get that work volume using MATLAB M script. You can try that by having 3 loops in for loop, which is one involving the outer loop for theta 1 varying from 0 to 90 and the other two joint angles theta 2 and theta 3 from 0 to 180 degree. Thank you very much.